What do you think a pendulum, a vibrating guitar string, and a bouncing spring all have in common? Well, they all share this really beautiful rhythmic dance called simple harmonic motion. Today, we're going to break down the energy that actually drives this constant, predictable back and forth. Okay, let's start with a picture we all know, a kid on a swing. At the very highest point, they're motionless, just for a split second. Then they swing down, going fastest right at the bottom before slowing down all the way back up again. This whole movement is the perfect setup for our big question. Where does all that energy go? How does it transform from one moment to the next? The answer lies with two key players, and they're locked in this constant, seamless dance. Think of them as partners in a continuous trade-off. We've got kinetic energy, which is the energy of motion, and potential energy, the energy that's all stored up, just waiting to be released. If you can understand this trade-off, you've unlocked the whole concept. So first up is kinetic energy. On our swing, this is that whoosh moment, right? The speed is at its absolute maximum right at the bottom. That's the equilibrium point, and that's where you find maximum kinetic energy. But then, way up at the top of the arc, where the swing pauses, the motion stops. And just like that, the kinetic energy drops to zero. Its partner is potential energy. This is all about stored energy. It's highest at the very top of the swing's path, where gravity is just dying to pull it back down to the center. It's kind of like a stretched rubber band. It's just full of potential, ready to snap back. So just look at this. They're perfect opposites, like a seesaw. When kinetic energy, our energy of motion, is cranked all the way up in the center, potential energy is at zero. And when the swing hits the edge and stops, potential energy is maxed out and kinetic energy is gone. One is always handing the baton to the other. Okay, so here is the absolute key to all of this. In a perfect world, a world without friction or air resistance, what physicists call an undamped system, the total energy is always constant. It never just disappears. The system isn't losing anything. It's just endlessly swapping energy between those two forms. And this graph just makes it all click into place. See that red curve? That's our kinetic energy, our speed energy, peaking right there in the middle. And the blue curve? That's our potential, or stored energy, which maxes out at the edges. But now, look at that green line right across the top. No matter where you are in the motion, the red and blue will always add up to that same constant total. The energy just changes its costume. All right, we've got the concept, we've got the visual. Now let's see how physicists capture this whole beautiful dance using the language of math. I know these equations can look a little intimidating, but trust me, they're just telling the exact same story we've been talking about. So this is our formula for kinetic energy. Don't get bogged down by all the letters. Just focus on that part in the parentheses. It's basically saying that your kinetic energy is highest when your current position x is zero, right in the middle. And as x gets closer to the maximum distance, x naught, that whole term gets smaller and the motion energy vanishes. The math just proves what we saw with the swing. And the formula for potential energy? It's even simpler. It's just telling us that the farther you are from the center, x, the more energy you've got stored up. That's really it. At the center, x is zero, so your stored energy is zero. At the edges, x is at its max, and so is your stored energy. And here is where the magic happens. When you add the kinetic and potential energy formulas together, those messy x squared terms, the parts that are always changing, they perfectly cancel each other out, and you're left with this clean, simple formula. The total energy only depends on things that don't change, the object's mass, its rhythm, and how far you pulled it back to start. That's why the total is always the same. All right, that's enough theory. Let's get our hands dirty, plug in some real numbers, and see these formulas in action. So, here's our scenario. We've got an oscillating particle. We need to figure out its total energy and then see exactly how that energy is split between kinetic and potential when it's halfway to the edge of its motion. The process here is actually pretty straightforward. First, you calculate the total pool of energy that the system has to work with. Then, you use the kinetic energy formula to find out how much of that pool is being used for motion at that one specific spot. And whatever is left over, well, that has to be the potential, or stored energy. The numbers you see here walk you right through it. Okay, let's do one more round just to make sure this is locked in. It's your turn. Now, this problem has one tiny little twist. We're given the frequency in hertz, not angular frequency. So we just need to do a quick conversion before we can get started. It's just one simple extra step.
So after that quick conversion to get our angular frequency, the logic is exactly the same. Find the total energy first, then find the kinetic energy at that specific point, and the potential energy, it's just whatever's left over. Remember, it always has to add up to the total.
Okay, let's put the calculators down for a minute and switch gears. It's time for a quick challenge round to really test our conceptual understanding of all this. First one up, we're given a spring's stiffness and how far it's stretched. The question is, what's its maximum stored energy? Just think for a second. Where in the motion would that happen? And you got it. It's at the point of maximum displacement. At that exact instant, 100% of the system's energy is potential. So the maximum potential energy is actually the total energy. We just plug in the numbers and we get a clean 1 joule. Okay, question 2. This is a pure logic check, no calculator needed. What's the kinetic energy right in the middle of the motion?
And there's that seesaw concept again. At the dead center, stored potential energy is 0. So all 4 joules of the system's total energy must be in the form of motion, as kinetic energy. The answer is simply 4 joules. All right, for our final challenge, let's try working backward. If we know the total energy and how far the spring stretches, can we actually figure out how stiff that spring is? You bet we can. We just take that total energy formula and rearrange it to solve for K, the spring stiffness. It just goes to show that by understanding the energy, we can start to uncover the physical properties of the system itself. So we've explored this perfect, frictionless dance where energy is always conserved, which kind of leaves us with one final thought. What happens when the real world, with all its friction and air resistance, steps in, and the music finally starts to fade?